Okay, so let's talk about the action potential. So to recap for resting potential, we talked about that Hodgkins and Huxley recorded from the squid giant axon, and that they found that it is more negative on the inside and more positive on the outside. And they called this the resting potential. And then they found that when they stimulated the squid giant axon, they got what they called the action potential. Right. And so they have this differential distribution of ions that they figured out between the outside and the inside of the membrane of the neuron. And that if you have this differential distribution on either side of a semi-permeable membrane, that you set up an electrical difference across the membrane. And this can act like a battery, right? So in a neuron, you do have this semi-permeable membrane, and this situation is mostly negative on the inside because of the actions of the sodium-potassium pump, where it's constantly pumping 3 sodium out of the cell, and it's pumping 2 potassium into the cell, which makes the resting membrane potential about minus 70 millivolts. Okay, so it's more negative on the inside than it is on the outside of the neuron. You need 2 reference points, remember, to look at any electrical gradient, and here you do have an inside versus an outside. And then we talked about squid ions. So for the squid ions is where we're going to start our conversation about the action potential. So for the squid ions, you've got potassium that's higher inside the cell and sodium that's higher outside of the cell. Okay, so squid ions then. If you see here, the ion potassium in the axoplasm, which is another name for inside the cell, or the cytoplasm, it's what's inside the axon, is 400. Normal blood, in terms of equivalent, would be 20, and seawater would be 10. Okay, for sodium inside the axon is 50. Normal blood is going to be 440, and seawater is high as well. And chloride here, you can see normally is kept low inside the axon and higher in a regular situation. So in the axoplasm, you have high levels of sodium and you have high levels of potassium, and you have low levels of sodium and here chloride as well. Okay, so remember, the sodium and the potassium are not free to move across the membrane as they will. They can get through, but there are active processes that have to happen to get them to go across the membrane. Chloride, on the other hand, is relatively freely moving, so it can pass through without having these active processes. And this becomes important to the action potential. Okay, so we're going to talk about a model here. And this model is basically the reason that we know that these things are true about the differential distributions of these ions and how they drive the action potential. So when you have a model in science, it's something that you say that's kind of a metaphor or a simile. In literature, it's kind of the same thing. So you have a complex process and you try to make a model to draw a parallel between it and something more simple. So this is a model, this Nernst equation. So this is Nernst here, who came up with this model and basically put it out there as a model for what he thought was happening in terms of the differential distribution of these ions on either side of the membrane in the squid giant axon. So it is a model that can predict the voltage anywhere based on the concentration of charges on one side of the membrane versus the other side of the membrane for one particular ion at a time. So anytime you're in a situation where there is a membrane and there is a differential distribution across the membrane of charged particles, I could use the Nernst equation and I could tell you what the voltage is across that membrane if I knew what the concentrations of this ion are both inside and outside. So in science, when you come up with the model, as Nernst did, then you put it out there, and a lot of people have the opportunity to work on it, to prove it right, to prove it wrong. And so this really drives the field forward in a way that Nernst did with this equation. So everyone kind of jumped on this. Some people excited to see something that works, some people excited to prove that it didn't work. So everybody's working on kind of validating if this model actually works. So here is the equation that I want you to see. So it's got 3 components to it plus a constant. Okay, so the V here is going to be voltage, and then you have plus or minus 60 log. This is the constant. So this is the number that has about 5 different variables all kind of crunched in together, like temperature and other things. And then this is just a number that we'll put in there. And then you have the concentration outside. So we're going to look at potassium here. So Ko is going to be potassium outside the cell, and then Ki is going to be potassium inside the cell. So I'm just going to kind of write this up for you so you see it. So we have the voltage, that's the V, equals this constant. Now, the constant, whatever this number is, what's important for you to know is that it is either going to be positive or a negative number, this constant, based on whether the ion that you're looking at is a positive ion or a negative ion. So for potassium, this is going to be a positive constant. And then you're going to have the concentration. So the concentration here, we're just going to say potassium outside, and then you've got your concentration of potassium inside. So this translates into this plus or minus 60 log of K out and K in. This would give me the voltage that I would expect across a membrane if I knew how much potassium was outside and how much potassium was inside. Okay, so let's say that if I know one of these and one of these, then I can figure out this one. But you know how math equations work. As long as I know 2 out of these, I can kind of predict what the other one will be. So if I know the voltage and I know the potassium inside, then I can tell you how much potassium should be outside. And you can do this to figure out any one of these. You can use this not just for potassium, but you can use it for sodium, and you can use it for chloride. All right, this makes the assumption that these molecules are free moving. So these ions have the ability to come and go through this semi-permeable membrane as they want to. They follow their gradients of concentration and they follow their gradients of electricity. Okay, but we know now that this is not actually the case because we talked about this idea that there is the sodium-potassium pump. Okay, so let's say what would happen to this particular equation here if we took example of something that is freely moving. So something that is freely moving in this system is going to be chloride. So for chloride here, when you run this equation, so instead of having the potassium here, you put the chloride here. And chloride is negative, so that means you'd use a negative constant here. Chloride, basically, when you do all this math, you get something that says that the voltage should be minus 69 millivolts if the chloride was able to go where it wanted. Okay, and what's interesting is that this is right about resting membrane potential. So we said resting membrane potential was minus 70. So this makes sense. This kind of proves or provides support for the Nernst equation that this is indeed what's happening. Okay, it's really close to minus 70. So if we have this over here, where we have, again, millivolts here, and we have time here, and we're going to have our action potential, this right here actually is going to be minus 70 millivolts. This is our resting potential. And so chloride will be right about where we would expect, minus 70, so minus 69 here. Okay, so let's talk about our other 2 players. So if we have a situation where we're going to talk about sodium. Remember, sodium is a positively charged ion. So if that's the case, we're going to use sodium here. And it's going to be actually a positive constant because it is a positively charged ion. And when we do this, we will find if we solve this equation for the voltage, knowing the inside and outside concentrations, the voltage, if sodium was a freely moving ion able to go wherever it wanted, it would be positive 57 millivolts. Okay, why is this important? Because we said that when an action potential happens, we actually have a spike up, okay? And this spike up is going to go pretty close to positive 57. Okay, so this is kind of where you expect sodium to actually be freely moving if this is what's actually happening in the action potential. Okay, that's sodium. We have one more player that when you talk about, which is our potassium. Potassium then, remember, also positively charged. So potassium here is going to be in and out. This is again going to be positive. And for potassium, if potassium was able to be freely moving, then potassium is happy here, where you'd have a resting membrane potential of minus 78. So really different from sodium. We know that these two are not freely moving, but we also know that this right here, if you allow this to do the regular shape of the action potential, that this right here is going to be pretty close to minus 78 millivolts. And so this probably is something to do with potassium. So where potassium is happiest freely moving based on the Nernst equation. Okay, so from these, we can say, okay, if resting millivolts here are minus 70, chloride probably is pretty freely moving in the system. We know that these guys are not freely moving. We know that the sodium-potassium pump is a thing, and we know that it's changing the distribution all the time in all of our neurons, pumping really hard to keep sodium out and to keep potassium in. Okay, so Nernst comes up with this lawful way to do these equations. And if you go back, you have a situation here on the bottom where you have sodium, potassium, and chloride, and you can see the math that allows us to get to this particular point. Okay, so let me do some drawing, and we'll try to figure out exactly what this means. He's explaining this lawful distribution of the ions across the channel, how you can use it to across the membrane, and how you can use it to predict the voltage at any given time. So when people start to prove him right or wrong, they basically have to manipulate one of these three variables. They can manipulate the voltage, they can manipulate the sodium or the potassium or the chloride outside the cell, and then they can manipulate how much of that ion is inside the cell. And we already said if you know at least two of those, then you can predict what the third would be. And so if this works, you would be able to manipulate each of these and be able to predict kind of in this triangle what the others should be. Okay, so you can do this by putting, so if you, let's say it's potassium. If you spritzed some potassium into the cell, so you can actually take these little electrodes and you can deliver things using them. Okay, so this would change the amount of potassium inside, and it should change the other two parts of this equation. You can bathe a neuron in an extracellular fluid that has a certain level of potassium in it as well. That's pretty easy to do. And you can look at the others. And in terms of the voltage, you can certainly use the voltage by change the voltage by holding it steady, by changing the difference between the inside and the outside electrodes, and decreasing or increasing the voltage in between them, or the difference in between them. So this is why his model was so useful for us. So when we give the axon just a tiny bit of electrical stimulation, let me show you what happens inside the neuron. So we said you can modulate the voltage. Let's do the same thing here where we have time and we have millivolts. All right, so what I'd like to do here is say, okay, this is going to be minus 70 millivolts. This is going to be a resting potential. And if you give a little bit of stimulation to this neuron, you might see this. And if you get a little bit of more stimulation, you might see something like this, and a little bit more like this, and a little bit more like this, and a little bit more like this. What's important here is that this doesn't happen forever and ever. This kind of incremental increase every time you have a little bit more stimulation. There is a certain stimulation that you can get to that will elicit this entire spike, the action potential. And when that happens, it actually does this. Okay, so this, whatever that number is, which we're going to work with about negative 55 or so. So when you get to about this threshold, the threshold is kind of just like a threshold is between like two rooms. You're entering one room or one state, coming from a different state. Okay, so this particular threshold happens because of something called voltage gated channels. All right, so voltage gated channels are really important because without them, we wouldn't have the action potentials the way that they are. So a voltage gated channel. Remember a picture of the sodium potassium pump? Okay, so there's a membrane on the outside of the axon, and there are pores or holes, what we call channels, going from the outside to the inside, right? And they can let things through. So there can be like a little hole in the middle that allows things to go through the center of this channel. And often these channels are closed. And if they're closed, it means that hole is closed up, right? So there's something blocking it so ions can't get through. So they're usually stuffed up. And this is what is the gated part. So something is gating them. So it's making it so that they're closed, right? So when it's closed, it doesn't let any ions through. It's gated shut. Okay, so what causes them to open? In this particular situation, the voltage is what's causing them to open. So when the membrane, or the difference between the inside and the outside, reaches a certain threshold, all of a sudden these voltage gated channels open their pores in the middle. So whatever is blocking them at the gate, it moves, right? It gets out of the way because it's reached a certain threshold of voltage. And when this happens, things can pass through the channel, right? So when they open up, they allow ions to go through them. And they're specific to certain ions. So if you are a sodium channel, it is a sodium voltage gated channel. Or typically the way that we say that is we put voltage gated and then whatever the channel is, voltage gated sodium channel. When it opens up, it will only allow sodium ions to pass through. There might be another channel called a voltage gated potassium channel. When that channel reaches the voltage that it will open, it will only allow potassium ions to pass through it. Okay, so this is important that they only allow one kind of ion in, and it's important for you to also know that the voltage at which their gate opens changes depending on which channel it is, whether it's a sodium channel or whether it's a potassium channel or some other kind of channel. Okay, so let's say this is a voltage gated sodium channel. If you have a situation here where the cell has hit threshold at minus 55, and that is the voltage that opens up the gate on the sodium channel, then the sodium can pass through it. Okay, there's no active thing pushing it through within this channel, out or in. Instead, it's just basically it opened and it's like a free-for-all. And so we've already said that there are much higher concentration at rest of sodium outside the cell. So you have a situation where you hit this threshold of voltage, the channel opens, and all of a sudden the sodium is free to move. It's free to follow its own concentration gradients and its electrical gradients. And so when this happens, it's going to follow both in a really robust way. It's going to be outside, okay? So there's no sodium really inside. The equilibrium here chemically is that it's going to want to rush into the cell. We already said too that sodium is a positively charged ion and it's negative outside the cell. And so the electrical gradient also means that there's a really powerful driving force for sodium to go through into the center of the cell. Okay, so you're gonna basically have what we call sodium influx. And the sodium influx, all of these positive sodium ions are gonna rush in. And when this happens, it's gonna drive this really high. Okay, so the inside of the cell, then relationship to the outside of the cell is going to be really, really high. And you can see it's going to go up here until it's about the level where sodium would be predicted by the Nernst equation if sodium were a freely moving ion. Because for a minute, for a brief second in time, sodium is a freely moving ion. Okay, so sodium goes into the cell because there's a chemical gradient, and it goes into the cell because there is an electrical gradient. So both these gradients cause the sodium to go in. And this idea of where is the sodium going, remember, sodium influx is what starts this action potential. It's going to kick things off. All right, so if you think back to chemistry class, we want to remember that all these channels, we've got a pore here in the center. And right, so we're going to have our phospholipid bilayer. This is the outside of the cell. Out and in. And you're going to basically have this channel here in the middle. So the inside of cell, outside of cell, you have a little gate here. And when you hit threshold, the gate basically is removed. And the way that this happens is that this channel is made out of proteins. Okay, and so the proteins might kind of all be in a circle or a ring, and they are clustered together like in a hexagon or a ring with a hole in the middle. And when you have the voltage shift, okay, or change, this actually shifts these proteins. It puts force on them and they shift just a little bit. And when they shift, this creates enough space for this channel to open. When they shift over, there is a hole in the middle that opens up that wasn't there at the lower voltage. Okay, and that will allow all of these sodium ions to come rushing into the cell. So sodium comes in. And it happens because of this conformational change in the proteins that make up the actual channel itself. All right, so at threshold, there's enough electrical change to allow these proteins in the channel to change their shape. It's incredibly well designed, so it only allows the one kind of ion in. In this case, it's going to be a sodium ion. The sodium ion starts shooting into the cell because it's positively charged and it's less concentrated inside, so it wants to equilibrate. So when it comes in, then you end up having the inside of the cell become a lot more positive. Okay, so somewhere in here, as the cell becomes more positive, a second group of channels are activated. And the second group of channels are voltage-gated potassium channels. Okay, so we're going to say potassium is red here. So this is where your sodium ions are open. Here, all of a sudden, potassium voltage-gated channels are open at a much higher voltage. Okay, so the result of this is that a separate kind of channel will open in a different channel, not the same channel as the sodium ones. And when this happens, there's the pore going through. The potassium has been stuck inside the cell, and the potassium will rush out as soon as the voltage happens, so that the voltage-gated potassium ions can go through the voltage-gated potassium channels. They will go out. So they were in, and they're all going to go out. Okay. The sodium influx happens when we're going more positive. This is the potassium efflux or efflux. So the sodium comes in, the potassium leaves. And that is the basis for the action potential. Okay, so remember the sodium potassium pump has been pumping as hard as it can to keep sodium out and potassium in. And as soon as there's an opportunity made by the voltage change in the membrane that allows the channels to open, then at that point, things can go where they're freely moving. And when this happens, the sodium here, sodium here stops coming in. and the potassium goes out. Right, so sodium all comes in, going up like that. This decrease here is the potassium going out. So this negativity that we're having a drop. So positive is because sodium's coming in. Sodium's a positively charged molecule. When it comes in, the cell has a increased potential in terms of voltage, right? So it's not as negative inside. Once you let the positive potassium out of the cell, you're going to start to lose positivity inside the cell because all of your positive potassium are leaving. Right, so this is what starts this drop here. The sodium influx comes in and it makes it more positive, but as soon as the positive potassium starts to leave from inside the cell, this starts to make the cell be more negative on the inside. Okay, and then eventually when this happens, then the sodium is not going to be able to come in anymore because those voltage gated sodium channels are going to shut. They're not going to be at a voltage that allows them to stay open anymore. And then the potassium continues to leave. And so the potassium then also has they're not going to be able to have their voltage gated channels open anymore either because the voltage won't be right for it anymore. And eventually they will shut too. But before they do, they overshoot. Because if you remember, the Nernst equation predicted that freely flowing potassium will be even more negative than the resting potential. It predicted a minus 78. Okay, so this overshoot here then is the result of the potassium coming in, being freely floating, but then the potassium channels are also going to close because the voltage of the cell won't allow them to be open anymore. And then as soon as the voltage goes, kind of overshoots, it'll come back because now all the channels are shut and they're just kind of sorting people back where they're supposed to be. And the sodium potassium pump will bring that back to the resting potential of minus 70 millivolts, because throughout this whole process of the voltage going up and the voltage going down, that trusty sodium potassium pump has been constantly pumping 3 sodium out and 2 potassium in to maintain this uneven distribution. Okay, so I've redrawn this because my board was getting a little bit messy. And I want to show you that if we have minus 70 here as the resting potential, and we have this characteristic kind of action potential shape, that each of these things are actually driven by an underlying cause and they have specific names. So the first thing that happens is that we have to reach threshold. So we have a little bit of stimulation. When the stimulation is high enough, at about minus 55 millivolts, we cross the threshold and then we will have an action potential follow. So this first thing that happens is that the voltage gated sodium channels open and sodium comes into the cell. So sodium comes in, and this is called depolarization. The depolarization word comes because minus 70 millivolts is very polarized. It is very far away from 0. So the difference there between the 2 points that you're measuring is high, right? So the depolarization means that you are becoming less polar, right? You're going closer to 0. So this whole thing here is the depolarization where the sodium's coming in. All right, at some point the sodium is coming in and the voltage is going up, and the voltage actually will hit the voltage gated potassium channels at the voltage that they need to open. When the voltage gated potassium channels are open because the voltage is reached, that's the correct voltage to open the pore in the channel, then the potassium will exit the cell. Okay, so potassium out. When the potassium leaves the cell, then the potassium is going to, this current is going to cause this to repolarize. So this idea that when the potassium goes out, the positive ions are going out and the cell will then start to become more negative. This is this whole downward slope. So sodium causes the depolarization, potassium causes the repolarization. Okay, so then at some point when the sodium and the potassium are going in and out, they will hit a different voltage, all right, because of the movement of these ions. And when this happens, then the channels will close and they won't be able to be open anymore. And the sodium will stop coming in, the potassium will stop going out. And when this happens, it takes a little bit of time for the sodium potassium pump to put things back where they're supposed to go. So this area right here, this is called hyperpolarization. So hyperpolarization then is going to be this area where it overshoots going back to resting potential. Okay, it does this because remember, a lot of negativity inside the cell here when all the potassium leaves. And so while all of the sodium's going in and out and the potassium's moving, the sodium potassium pumps are working this whole time. They are working all the time during an action potential, not during an action potential, and they're always trying to shove the sodium out, and they're always trying to bring the potassium in. So 3 sodiums out, 2 potassiums in. And because of that, this allows you to go back to the resting potential of minus 70 millivolts. So they're basically cleaning up the mess where there was too many sodiums coming in and too many potassiums going out. And so you're not at resting potential anymore. Where the cell is happiest, assuming that we're having working sodium potassium pumps, is minus 70 millivolts. So this hyperpolarization is where this kind of balance becomes restored. Now, when you have an action potential, you have this area called a refractory time period or a refractory period. And the refractory period is basically the time that it's like spent putting things back to where they're supposed to be. So that if you were to get another stimulation to that cell, it would not be able to give another action potential because it's in the refractory period. So typically this area here is the refractory period. So even if you stimulated it here, you still couldn't cause another action potential because things are still getting back to where they're supposed to be in order to have all systems go to do another action potential. So you can hit it really, really hard here, like with more current than you usually would, and you can sometimes get action potential to happen during the hyperpolarization. But if you hit it during the actual action potential, it wouldn't make a difference because you're already kind of in the middle of the opening and the closing that already has to happen. Okay, so this takes about 2 milliseconds to have this action potential happen. So that means that you have about a window of 2 milliseconds in between when a stimulation will give you another action potential, or it'll be in the refractory period, you won't be able to do it. So the other thing that's important to know about the neurons is that action potentials are all or none. So we have what's called the all or none law. So every time you have an action potential, that neuron will have an action potential that's the same size, the same shape, and it moves at the same speed down the axon. So all action potentials are identical. If you have a situation where you have some bright lights and you have an action potential in response to the light, if the light was brighter, you would not have an action potential that was more robust or longer or higher, right? You would maybe have one cell give more action potentials, or you might have more cells give an action potential, but you would not have a change in what that original action potential would have looked like. Okay, so it's either there, it's not there. If it's there, it has the same size, the same shape, and the same duration. Okay, so a single action potential, it's important to know that it's pretty much meaningless noise. So the way that we kind of interpret action potentials is actually the information in the nervous system comes from the integration of all of the action potentials that one neuron gets, that then determines whether or not they respond or don't respond to the signals coming in. So the action potential is the building block of neuronal communication. But what happens down at the synapse? So we talk about this. The axon goes towards the end, which is the axon terminal or the terminal bouton. And there you have the ability to transmit, communicate this information to the next neuron. And so we're going to move next into exactly kind of how this happens in terms of what happens at the end of that first neuron, what happens in the space between the first neuron and the second, and then how does that second neuron have the opportunity to react to this and to integrate information it's receiving from all the synapses that it contains on its dendrites. Okay, so thank you very much for listening, and I will look forward to talking to you next time about the synapse.